Hello, everyone, and welcome to today's talk on the exciting topic of cryptography. I wanted to start with this, and if you don't remember this thing, it happened, seems like a lifetime ago. It happened before the pandemic, back in, I think, January this year, which was, well, not too long ago, but at the same time, it feels like it's been forever. Anyway, somebody found an issue in cryptographic implementation in Microsoft Windows. And it was a pretty big one. Um, the, the problem was with validating signatures, validating certain things that would potentially allow an attacker to do all kinds of bad things. For example, intercept and modify HTTPS connections, send some files to the user that they would install thinking that the files were updates from Microsoft. In fact, they were not, and so on. Why did I want to talk about this? So if you read about this vulnerability, you probably noticed that the problem was not actually in like the fundamentals of cryptography. It was not a problem with a certain algorithm. It was not a problem with some cryptographic scheme. It was not a problem with a protocol or whatever. It was just one or two simple mistakes in a particular implementation, right? So why this talk today? We all agree that cryptography is hard, and it is hard on multiple levels, from like understanding what's going on to like implementation itself, and then there are so many ways to make a mistake. And mistakes are bad, right? We all agree on that. And today we're going to talk about how to exploit some of these mistakes in crypto. We're not going to talk about 0 days. Um, There's no information about that in this presentation. There will be no complex math at all. There will be just a few really basic things. We're not going to talk about the dark future of cryptography, which is probably quantum stuff that's going to break everything. And we're not going to talk about how to break correctly implemented crypto, because by definition, it is unbreakable today. Might be breakable tomorrow, but today, if everything is implemented correctly, it is unbreakable. So my name is Alexei, and I'm a software developer in the past. I spent over a decade writing code, primarily for one big company. And then I kind of switched gears and started doing more security stuff in application security world, starting in the same company and then moving into some security consulting. And I currently work for Salesforce. I have several certifications in security that are listed here, but the most important thing on this slide is this. I am not a cryptographer. So I don't consider myself a cryptographer. I probably don't know much about it. I just come to this topic strictly from practical perspective as a hacker. And you would realize going through this presentation, there is nothing really deep and complicated here, but there are some practical things that we all can do in order to exploit some mistakes. So general recommendations up front. When doing crypto, we need to use well-known and secure algorithms, right? We all know that we are not supposed to use DES because DES is no longer secure. Okay. The second thing is we should use standard and stable libraries, meaning good implementations of those algorithms, right? We don't use some obscure library, some code that you downloaded from who knows where, and just run it. You pick up a library that's well known, that's well maintained, and does not have known security bugs. The third thing is very important. We need to follow the best practices. And that's basically a very broad and deep topic. And it really depends on what cryptographic scheme you use, what algorithm you use, what you're trying to do. There are certain things that we all need to understand and follow. And the last but not least, do not invent your own crypto. And you have heard this advice hundreds of times, but just wanted to throw this in here again. In terms of common mistakes, the first one is insufficient entropy, meaning there is not enough randomness. And randomness in crypto is very important. Many times when we deal with cryptography, we need a good random number generator. And when we look at some data, the data might look like a random noise. And that's great. That's awesome. Anything in those cases that doesn't look random enough is probably an indicator that things are not done right. The second one is algorithm choice, meaning we use a wrong algorithm. We use a chainsaw where we need a hammer, or vice versa. So that's very important to know and understand. And the third one, that relates to those best practices. So when we pick up an algorithm and that's the right algorithm for the right purpose, we need to understand what exactly we need to do here. Like if there's an IV, what's that IV? Where do we get it? And so on. Where do we get the key? How we store the key? What mode we use, and so on, so on. Number 4, it's often overlooked, but we tend to focus on confidentiality, right? We all want to protect the data. We don't want anybody to read it, but we often forget about integrity. So is the message trustworthy? Okay, we encrypted it, but can somebody actually modify it in the way that we don't want? So integrity is really, really important. And the last but not least is key management. You can do everything right, but if you don't manage the keys correctly, your keys get leaked, your keys get cracked, or obtained in some other way, and your whole scheme is broken. Okay, this is the math for today. Exclusive OR, or XOR. This is the only operation, a mathematical operation that I'm going to talk today. I call it the ultimate crypto weapon, and you'll see why. So, but before we go there, you all know XOR, but just to reiterate it here, here's a table on the right that kind of like on the bit level shows the operands and the results. And there are a few interesting properties of XOR. The first one is anything XOR with 0 is the same thing, doesn't change. Anything XOR itself is 0. And if A XOR B equals C, then A XOR C equals B, and B XOR C equals A. So that means you can move that operand to any side of the equation and it still holds true. Okay, let's talk about randomness. In terms of random number generators, there are 2 big classes of them. The first one is called true random number generator. And these are things that are non-deterministic and they create unpredictable results. The true random number generators are usually implemented with the help of hardware. So there is some input that is impossible to predict, like for example, ambient temperature or noise or I don't know, electric current fluctuations, you name it. But basically that's something that really does not depend on the computer itself. It's some kind of an input from outside that you can convert to random numbers. And there's also pseudo-random generators. These are deterministic, meaning that if you run it, if you give it a certain input, you know exactly what the output is going to be. And they're seed-based. So you seed a pseudo-random number generator with, like, say, a random number, right? And it will give you a pseudo-random stream. So why do we have 2 and not just 1? The problem is the true random number generators are pretty slow and it's very difficult to get a large amount of data from them. Pseudo-random generators are fast, and they usually used in together. So we use trng to get that seed, and then we seed prng with that seed, and we get a stream. All right. A few years ago, somebody decided to write a ransomware for Linux. The ransomware at that time was already popular for other platforms, and some people thought, well, okay, enough with hacking Windows. Let's attack Linux now. So they wrote this ransomware called Linux Encoder, and what happened is it was immediately, almost immediately, how to say, the people were able to find an issue with that ransomware because it depended on predictable encryption keys. They did not use good entropy source, and it was possible to decrypt all the files without paying the ransom. And let's see a demo for that. I do have a demo for that. By the way, a lot of this presentation today will be live demos. So follow up, and also at the end, I'll give you a link to the GitHub repo where you can download this code and play with it yourself and see what's going on, analyze it, modify it, do whatever you want. Okay, so we have a document. It's a text file that says not all random functions were created equal. Awesome. And we're going to encrypt it and ask for ransom. So now this document.ransom is some kind of binary data. Well, it's encrypted file. We don't store the key anywhere. If you look at the encryptor, you'll see that they seed the pseudo-random number generator with the current time, which is very, very bad idea. And why is that? Because this file that's written on the disk has a timestamp. The timestamp is with high probability exactly the same as the timestamp that was there at the time we were getting the seed. So in order to decrypt this file without knowing the key, all we need to do is to get the file modification timestamp and use that as a seed for random number generator and decrypt the file with that. So let's see if that works. And it worked perfectly. We were able to successfully decrypt the data, and we got the original text. And that's exactly what happened with that Linux encoder ransomware. They used the current time to see the random number generator. Again, very bad idea. And here's a good advice. Of course, it's sarcasm. Doing MD5 on current time does not give you any advantage at all. So again, this is bad advice. Don't use time. Okay, let's talk about encryption algorithms. There's this encryption algorithm that is not used these days. It's called one-time pad. Let's say we have a message M and the key K. The encryption would be a simple XOR operation. So the ciphertext here, C, is M XOR K. And that's it. That's all there is to this encryption algorithm. And how is that even encryption? Well, there's a theorem that says that if key is random, then the key XORed with anything will also look like random. And there is no way to recover the original message just by having the ciphertext. Well, decryption, due to the properties of XOR, is the opposite operation. So we just XOR the ciphertext with the key again, and we get the original message. So this is very, very simple algorithm. And here's just an example of ones and zeros in the message, and in the key, and in the ciphertext. So why is this algorithm not used these days? Well, the obvious problem is that key has to be as long as the message. So if you want to encrypt a gigabyte of data, your key has to be 1 gigabyte long, and that's very impractical. The second problem is in the name. It's called one-time pad for a reason. Why one time? Well, apparently, if you encrypt 2 messages with the same key, there's an issue. If somebody intercepts those ciphertexts, they can XOR them, and due to the properties of XOR, the key would cancel out, and they would get an XOR of the original messages. This might not seem like a big issue, but it is. And because again, the attacker can gain a lot of knowledge from just intercepting ciphertext. And in some cases, that's enough to break the scheme. Okay. These days we use, instead of one-time pad, we use stream ciphers. So what is stream cipher? Instead of having an infinite key, we have a finite key, and we give it to a generator function. This is basically serial random number generator. So our finite key of, say, 16 bytes becomes an infinite key stream. And then encryption is the same as in one-time pad. We just XOR message with that key stream. And decryption is, again, the same thing. We XOR ciphertext with the same key. But again, we can see here that we should not reuse keys because, again, we'll have 2 messages encrypted with the same key. We XOR them together, and we get the, we XOR the ciphertext, and we'll get the XOR of original messages. I wanted to know that modern implementations of stream ciphers do introduce some randomness. So it is, these days, I would say it's safe to use the same keys, but in the classic sense, we should not. Yeah, I mean, there are additional ways these days in modern implementations to protect from these kind of attacks. But let's see what happens if we use an older algorithm and encrypt the same message with the same key. I mean, two different messages with the same key. Okay, I have a visual example here. I have 2 pictures. One picture is of myself, and the other picture is of a smiley face. Cool. So let's try to encrypt these 2 images with the same key. Okay. All right. So now, in addition to these 2 images, I also have two other images that look like random noise, and these are encrypted images. Like, if I just look at one, I cannot tell anything about it. Like, it really looks like random data. Okay, looking at the source code, we're using RC4 algorithm, which is, again, it's an older algorithm. I do not recommend using it today, but for the sake of this example, I'm using it here just to demonstrate. We generate a key once, and then we encrypt 2 images with the same key. All right, now let's see what happens when I XOR these 2 images. How do I XOR them? I'm going to open them in a graphics editor, and this particular editor allows me to do an XOR operation. So first thing I'm going to do is I'm going to paste 2 images as layers. Here on the right-hand side, you can see that I have 2 layers. The first one is the first encrypted image. The second one is the other encrypted image. This editor allows me to perform layer operations, and one of them happens to be XOR. It's right here. So if I XOR them together, see what happens. I, as a human, can immediately not see just one message, but both messages. I can see that one of them was a portrait of a person, and the other was a smiley face. so to me, it's immediately recognizable. So that XOR operation of the two ciphertext reveals both messages to me. Moreover, if I happen to intercept one of the original messages, like for example, if I happen to know that one of them was the smiley face, I can add it as a third layer and apply XOR operation again. And I get the original message that is a photograph. So again, I have three layers here: random, 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 and a smiley face. And when I XOR them three together, I get this. Like, this is mind-blowing, right? Okay, cool. You get the idea. Okay, in addition to stream ciphers, we also have block ciphers. So stream ciphers work on bits. You can encrypt single bit at a time. Block ciphers work on blocks. You give it a block of bytes and it does permutation based on the key and gives you ciphertext, which is another block. Well, usually the data we want to encrypt is longer than a single block. It's longer than 16 bytes or whatever, right? So we need to do something about that. The most obvious and most straightforward way to do that is just to split the message in multiple blocks and encrypt them all separately. And that might seem like okay, but if you think about it, if two plain text blocks like block 1 and block 3 happen to be the same, then the two ciphertext on the output will be the same. And so the ciphertext is no longer random. You can see patterns there. And again, patterns in cryptography are not good at all. Let's see what happens when we encrypt something with a wrong mode like this one, like this ECB. Again, I have a visual example. I have this image, which is a screenshot of the title slide for this presentation, okay? And I'm going to encrypt it, and this script encrypts it twice. First, it encrypts it with CBC mode, which we have not discussed yet, and it also encrypts it with ECB mode. And here is the script. It generates a key. It does not store the key anywhere. It encrypts files. It encrypts the file 2 times with different modes. So let's see what happens. Here is the image encrypted with ECB mode. As you can tell, even though it does not exactly look like the original image, you can completely understand what was there, right? We as humans can immediately, like instantaneously analyze it and just so-called decrypt the original message, right? In contrast, here is the CBC encrypted image. And that looks like random noise to me. And there is no way for me to understand what's going on here. So what is this CBC? The CBC introduces randomness for every block. It uses result of previous block encryption. So it, like, for example, it uses this ciphertext to feed the next encryption operation. So the ciphertext is XORed with plain text, and then the whole thing is encrypted, and so on and so on. But for the first block, we don't have the previous block. So we need something else. And that something is called initialization vector, which is just a random number. And it doesn't have to be a secret. It just has to be random. So you generate it when you encrypt, and you can send it along with ciphertext. You don't have to encrypt it. But it's used to kind of seed that encryption operation to introduce randomness, and then you use it during decryption. So decryption is the opposite operation. at each step, the previous block is used to XOR with the result of decryption to get the original plain text. So if we have the encrypted message of 3 blocks, C1, C2, and C3, then the decrypted blocks would look like this, right? So we would decrypt a block, and then we would XOR it with, in the case of the first block, we would XOR it with IV. Second block would XOR with the first block, and third block will XOR with the second block, and so on. Okay. Now, one mistake that some people make, and I've seen it done. So this is not just theoretical, but it has been done, and it's not a good idea. So okay, we need this initialization vector, and we need the key. So we kind of need two inputs to our encryption operation or decryption operation. So why, the question is, why can't we just use the key as initialization vector? Well, for one, it's kind of random, right? And the second thing is it's secret. So we don't even have to send it across with the data, because whoever is receiving the data and decrypting it already knows it. So people try to cheat and do that, and this is not a good idea, because let's see what happens. Again, let's say an attacker intercepted an encrypted message consisting of 3 blocks. So if an attacker can modify the encrypted message and resend it, so it's a man in the middle, right? And resend it to the one who receives it and get something back as a result. So we consider certain assumptions here, which are often considered in cryptography. Like in this case, we can modify this cipher text, and we can also ask the decryptor to decrypt it for us. Okay, so the attacker builds this. Instead of C1, C2, and C3, they create C1, zeros, and C1. And then they give it to the decryptor. So when the receiver decrypts that, here's what happens. The result of the first decryption operation on the first block is basically XORed with the key, because key is the same as IV. IV is used, a key is used as IV. The result of the second block decryption is this, and we don't care what it is. But the result of the third block decryption is XORed with the previous block, and it's all zeros. So it's just this. Now, if we take that and this and XOR them together, we get the key. So if we can do that, not only like we cannot decrypt the message, but we can just get the key, and then we can decrypt the message. And let's do a demo on that. So for this one, that's not the right one. Okay, here it is. I have a web application that gives me a session cookie. So this session cookie happens to be if I look at the source code, let's assume the source code is open. Anybody can analyze it. So I'm looking at the source code. I see that the session is a very simple object. It has two fields, user and role, and for the guest user, which is me right now, the user is set to guest. And then when I go to this website the next time, this session cookie is analyzed, and if the user is admin, then I get access to the administrative page, and if not, I only get access to the guest page. Here we can see that the cookie is encrypted, and is encrypted using AES algorithm, which is a good algorithm. We use CBC mode, great, but we use key as IV. Let's see what can go wrong. So I have this cookie value that was given to me by the server. First thing I need to do is to build that really weird encrypted message, right? So instead of the original one, I get this, and those A's in the middle is our 0 block. Now I get that, copy that, and I refresh my page. So that now this new cookie value will get decrypted on the server side, and of course it's not decrypted properly because there's some garbage here. But the server is nice enough to tell me about it and even give me a base64 representation of the decrypted string. And all I need to do now is to put that into my other script to retrieve that key. So what are these forge and get key? The forge is like very simple. You know, we just build a message using 3 blocks. Okay, and the middle one is zeros. And the get key is, again, a very simple operation. It's just basically an XOR. This is a bitwise XOR. Now, how do I know that this is the correct key? Well, since I run the server on my machine, I can just print that session key, which is stored in the file, and you see that it's C4, F1, E0, FB, which is exactly matches what I was able to retrieve as the user who does not have access to the server. Cool. Okay, the other problem with block ciphers is it only acts on blocks, right? So you need to have your data, the length of your data has to be multiple of the block. So you can only encrypt 16 bytes or 32 bytes or 48 bytes and so on. But your message is not always exactly multiple of the block size. So what happens then? So what happens then is we use so-called padding. Let's say we have this message of 10 bytes, but we need 16 because our block size is 16. This is not good. By convention, we just pad that message with 6 extra bytes, and each one of them is set to 6. So when you decrypt this and you see that your last block ends with 6 sixes, then you can just throw them away. You truncate that message because this was padding, and padding works great for block ciphers. One problem with padding is, well, with implementations of decryption using block ciphers is padding oracle. What is padding oracle? So let's say your server who processes encrypted data. So you receive ciphertext, you know the key, you decrypt it, and then of course you would check the padding and to know whether you need to trim that message or not. And if the padding is not okay, it's reasonable that you give some kind of error message saying that your message was corrupt or whatever. If everything was okay, you continue. Now the problem is if you let the user know about this, they can basically decrypt anything without knowing the key. How is that possible? That might sound like a strange thing. How can you decrypt a message without knowing the key? Okay, I have a padding oracle here, which runs as a web application. This application accepts encrypted messages. It gives me an example. If I refresh the page, you can see that the message changes every time. Well, actually it doesn't change. It's just, it uses a random IV every time, okay? The key stays the same, but the ciphertext changes because of random IV. So if I click on this encrypted message gets sent in the URL and is decrypted by the server it gets processed. I don't know how it gets processed, but what if I try to change this last byte? It's 8. Let me set it to 0. Okay. And send it. If I send it like that, I get invalid message. The title says unauthorized. Okay, let's look at the code. The code just decrypts the message using AES algorithm, using key and IV, using CBC mode. Everything's good. It's unpadding that message to throw those padding bytes out. And it, of course, this is within try block, and it catches the value error exception, meaning something got wrong during decryption. And we just say your message was bad, unauthorized, whatever, right? And nothing like, just by looking at this code, you wouldn't assume that anything was done wrong here, but this is enough for an attacker to decrypt the message. Well, I already said it like 3 times. Let's see how it works. My exploit accepts this URL. And what it's going to do, it's going to retrieve that encrypted message here byte by byte. And it didn't take too long, did it? So here is the original message. Padding oracles are real. And as you can see, it started with the first block and starting with the last byte. And here's S, here's ES, LES, CLES, and so on. And then it proceeded with the next byte and retrieved the rest of the data. Like, how did it do it? Let me run it again. And this is the backend. These are the requests on the server. So basically, this exploit sends hundreds of requests to the server. Each time a single bit gets, well, a byte, is modified in a certain way. And by just trying different bytes, it either gets an error or like padding error or no padding error. And using that information, it's able to retrieve the original message. Here's the exploit. And we're not going to go into details on how this is implemented. You're welcome to study it on your own or contact me and I'll help you with that. But it is possible. It is real. And these attacks were implemented in the wild. And I mean, this is real stuff, not just theory. Okay, like I mentioned earlier, we often tend to focus on confidentiality and forget about integrity. Integrity is, again, extremely important. Let's say we send a message that says send $100 to Alice. We encrypt it, but an attacker intercepts it and modifies it. So when the message is decrypted, it says send $100 to Mallory, and Alice doesn't get anything. So is that possible to do even without knowing the encryption key? Is it possible to modify such message when it's encrypted, but you don't know the key? Well, the answer is yes, in some cases. This is often called bit flipping attack. And how does it work? If we use a stream cipher, and we remember that stream cipher is just a simple XOR operation. So let's say our original message was guessed. Maybe it's a session cookie, right? So we are guessed. It is encrypted. So the encrypted message is the original message XORed with the key stream, right? Okay. So attacker intercepts this message, modifies it instead of the original. So that ciphertext gets XORed with guessed because the attacker knows that it says guessed. But the goal here is not to decrypt it because it's already known. The goal here is to modify it so the unsuspecting server thinks that I'm admin, right? So, okay, I XOR it with guest and XOR it with admin. Why am I doing it? Now, let's see what happens on the server when this message is decrypted. When it's decrypted, it's simply XORed with the key stream, okay, which expands to this. So this new ciphertext is basically this thing, okay? Now this original ciphertext is expanded to this. Now guest and guest cancel out, keystream and keystream cancel out, we get the admin. And I do have a demo for that. Okay. Again, I have a very simple web application. This time it's giving me session cookie encrypted differently. Not like here, right? But if I delete this cookie, let me see if I can delete it, yep, and refresh the page, I get a different cookie value. Well, basically it's the same data encrypted again. It's just encrypted using a new stream cipher called Salsa 20. And I'll show it to you. Here's Salsa 20. And this implementation is using nonce. Nonce is that randomness that I mentioned that is introduced in stream ciphers. So, you know, to help with stuff like key reuse. So, okay, but in this case, I don't even care what the nonce is. I don't even care what the key is. I can still modify this message because there are no integrity checks here. When the message is decrypted, it's decrypted right here, right? It's just converted to JSON, and I mean from JSON to internal object, and then it gets validated against admin. All right, so I can use that bit flipping attack. My exploit just gets that ciphertext. Again, it doesn't care about the encryption key or the nonce. It needs to know the original plaintext. I can look at the source code and analyze and understand what it is, right? Its user and the date, but conveniently it just prints it here, so I'm just going to copy it from here. And I need to put down my desired plaintext. The desired plaintext is admin. I want to be the admin. Moreover, if I look at the source code, I see that the date parameter is not even used. So I can just completely get rid of it. All right, so here's my new message that I want the server to believe. Okay, cool, bit flipping done. Here's my new cookie. Copy it to my browser, try it again. Now, if I refresh the page, I'm the admin. Well, it was easy with stream cipher, but apparently the same thing is possible with block ciphers too, because block ciphers are using initialization vector or IV. So especially if you're trying to modify that first block, it can be done trivially. And we're not going to go into details on this, but it's basically the same idea, because we XOR with IV, then so we can modify that IV and submit a new one, and our new message will decrypt to what we want. And I have a demo for that too, but I'll leave it up to you as an exercise when you go to GitHub and download my source code. So to ensure integrity, what we use is called authenticated encryption. Authenticated encryption ensures confidentiality, integrity, and authenticity. That means it is protected, like people cannot decrypt it if they don't know the key, but it's also protected that people cannot modify it if they don't know the key. The authenticated encryption generates a so-called authentication tag. And that authentication tag is verified during decryption. And if it doesn't match what it's supposed to be, then an error is generated and we did not proceed. We did not trust that data that is not authenticated. So very, very important to remember, again, when you do in crypto, make sure that you consider this, not just confidentiality, but integrity. In many cases, is not just as important as confidentiality, but in some cases, it's way more important. And the last topic that I wanted to discuss today is storing the passwords. 3 things. Number 1, we all know that we should not store plain text passwords, right? Because they can get leaked. Not a good idea. Rule number 2, we should not store decryptable passwords. Okay, we decided we're going to encrypt, but we should not use the encryption algorithms that you can apply to decrypt and get the plain text passwords, because sooner or later, your encryption keys will get leaked or compromised in some other way, and you'll get, the attacker will get access to the passwords. And rule number 3, we should not use one-way hash. And you might think, what? I thought everybody was saying that we need to encrypt passwords one way, right? Yeah, that's true, but some people take that advice literally and they use one-way hash to store the passwords. And why am I so specific about this? Well, there's a big difference between one-way hash and the other thing, which is also one-way, but it's called KDF, or key derivation function. That's the thing that we need to use for passwords. Here's the difference. Hash is cheap, meaning it's fast, right? Key derivation function is expensive. It can be expensive in terms of time or CPU usage or memory usage, and sometimes all of them. Why is it important? Is because if somebody's trying to crack your hash, they can do it easily if you use a one-way hash function like SHA-1, for example, or even SHA-2, whatever, right? Because it's, by definition, it's fast. They can iterate through thousands of, maybe millions of hashes per second. If you use KDF, it becomes really expensive. They can iterate through a handful of hashes per second, and it's very impractical. And just so you appreciate that, I wanted to show you a demo. I have a hash generator script, and it can generate SHA-1 hashes. I think it's SHA-1. Let me double check. Oh, no, it's SHA-256. Cool. Yeah, SHA-256 is a great hash algorithm. It's secure for its purpose, right? It's even using random salt. Everything is good, right? Here is the generated file. Here is the hash, right? Now, if I want to crack this, I can run different tools. In this case, I'm just running John the Ripper. Boom, and my password is Pink Floyd. And it only took a fraction of a second, right, to crack this password, because it's so simple. It's in the dictionary, and it's in this dictionary, and the tool was able to iterate very quickly. To show you the difference, let me generate a hash for the same password using PBKDF2. And just to mention, PBKDF2 is not even the latest and greatest of these, but just to demonstrate. Let me run John the Ripper on this. And you see it's taking longer already. First of all, it decides to run 8 threads to crack. and it's not returning yet. It's going to take a few more seconds in my, at least in my previous tests. It should eventually return. Okay, here, it returned. Yeah, the password is Pink Floyd. It was able to crack it, but it took way longer. It took like 23 seconds. And here are the stats. The tool was only able to iterate through 44 passwords per second. And in the first case, it was able to iterate through 100,000 passwords per second. You can see it's a huge, huge difference. So it becomes very impractical to do it for if you store the passwords using a good function. So takeaways. If you're a breaker, you need to understand the concepts of crypto on the technical level. Yeah, it's not just, I mean, sometimes it's enough to just know the basics, but in most of the times you need to dig a little deeper. You need to examine the industry guidelines. They are there for a reason. If they say a random IV needs to be used, then it's there for a good reason. And if you see that it's not being followed, then there's probably something wrong, and it could be exploitable. You can expand on other people's work. There are some tools, there are papers, there are talks, conference talks, and whatnot, and you can always use the experience of other people to build up on. If you're a builder, you need to understand the crypto concepts. You don't necessarily have to dig deep, but you need to understand why, what you're doing and your tasks specifically. Like if you're storing the data, you want to encrypt it, what algorithm you need to use, what keys, how you store the keys, what encryption mode you use, and so on and so forth. And of course, follow all the guidelines. Again, they're there for a reason. If we don't follow them, then we potentially open up ourselves to all kinds of bad things. And learn from other people's mistakes. Sometimes things get published, like if something was done wrong, like you can read about that and see what exactly was wrong. And don't do that. For further learning, I would highly recommend this course on Coursera. It's free. I'm not affiliated with Coursera or whatever, but I just happened to take this course a few years ago, and it was awesome. I believe it's still there. The second thing is there is this free book. It's like open source project, but it's basically a PDF that you can just download and read. It's awesome overview for in order to understand it covers lots of things, from really basic to some really deep stuff. Highly recommend. As I promised, my code is on GitHub. You can just go to this URL, download it, play with it, and let me know what you think. Let me know if you wanted to add something here. I would be happy to talk to you, and good luck in your crypto adventures.